start with your talk.
How things are going in Beijing? When we will be able to visit you in person?
These days is getting a bit better, yeah. But to fully open, you know, for international traveling, I guess it will need some time still, yeah. So in general, the situation in Beijing gets better, yeah. And I think there's also voice that there's at what time and when and how we have you know different strategy or open the international traveling, yeah. So far not too much change, yeah. Yeah.
I was traveling to Trondheim to Arne Brothers last week, and I was surprised at the airports nobody's carrying masks or something, so kind of COVID seems to be over. And here in Austria it's very fun because in the region outside of Vienna, when I'm traveling with train, we do not have masks anymore. But then when we cross the border of Vienna, then we should put masks in the same train. So it's but it looks like COVID slowly is disappearing from our life, so we don't see it anymore so often. Somehow they open.
That's
everything.
A good sign.
So I hope I think autumn will be an issue that there will be no new variant.
Yeah, totally. It will be really nice to have the conference in person mode. Yeah, that is what. Yeah, we can. Actually, 2 years ago, we didn't how to say imagine that after 2 years it's still difficult. Yeah, but this is the case so far. Yeah. I hope it will change.
Is it hard for you to travel to US or somewhere to some conferences, or you would prefer to stay for the moment in China?
Technically we can, but the returning is very difficult. Yeah, it's a lot of quarantine and things. Okay. Okay, let's start. So our first invite speaker is Professor Andrii Chumak from the University of Vienna, and his topic is out-of-plane nanomagnonics. Please, Andrii.
Thank you very much. And thank you very much, Jaime, for the kind invitation, for the opportunity to present here and this nice conference, our results. And it's really a pity that we cannot be in person in Beijing. I love traveling to Beijing a lot. We did a few times already and always use an opportunity, but I'm pretty sure so soon everything will come back to normal life and we'll be traveling. Yeah, so today I would like to present out-of-plane nanomagnonics. So it's one direction which I believe is new and maybe has potential in the field of magnonics. COVID kind of broken communication, and I did not talk to my colleagues much because of all this pandemic. Yeah, just to inform that I'm not anymore in the group of Burkhard Hillebrands and Kaiserslautern. Now I'm working in the University of Vienna, where I established my group, and I like this place, a very large old university. And if here you can see our group, so I'm very lucky to work with many young talented people. We have quite broad scope of research. Of course, we continue magnonics, particularly nanomagnonics, the scale of sub 100 nanometers. or so. But in addition, we also have expertise in superconductivity, primarily given by Alexander Dobrovolsky. And we have with quantum optics, Sebastian Knauer is from that field, and we now merge our efforts and go in the direction of quantum magnonics as well. But today I'm going to speak only about room temperature magnonics, and the person who obtained principally all the results which you will see today is Chumak, who finished PhD in Kaiserslautern, and now he's postdoc, the senior postdoctoral research in our group. And yeah, so that's what you will see. It's his the result. Yeah. So just since we are open for collaborations, just briefly what we have standard micro spintronics transport measurements. We have PPMS to do. We have access to PPMS to measure the same in broad range of temperatures and fields. We have brilliant light scattering spectroscopy. We are constructing. It's not so empty anymore, but we are building time result MOC, and we already have running 10 millikelvin fridge. To be able to operate with ultra low temperatures with quantum magnonics. And here you can see our key partners. So first of all, we do not have facilities for fabrication. We do all the job inside tech, and Mikhail Urbanek is in charge there. They have fantastic facilities, 2,000 meters packed with everything you want, 21 permanent staff, and it's only 2 hours to drive from our place. So we fabricate all our structures there. We keep collaboration with Philip Piro, with Burkhard Hillebrand in Kaiserslautern. If we go to data processing, of course, we keep contact to IMEC to know what is good, what is bad. Iron Garnet is still from Karsten Dubs. It's very nice, high quality liquid phase epitaxy nanometers a geek. Theoretical support primarily from Roman Verba. And we also now collaborate a lot with Dieter Zeus, who runs another group here at the same faculty. So this slide is motivation. You saw already many times. Here I put it like a brief report. So we went into this direction primarily in the frames of my ERC, which was over in December. And here's just a report of what we actually reached. The motivation is that CMOS is fantastic technology, which we use every day, no doubts, and it continues evolving, but evolution is getting slower. And people are asking what kind of computer we will have in 40, 50 years on a long-term scale. Will it be the same kind of device, but with more cores, or maybe there will be something else? And this kind of creates a super conditions for physicists to think about completely different approaches and to test them. And that what we do is named so-called wave-based computing, where instead of operation with scalar variable like charge density, here in electronics, we use a wave. And this wave has amplitude, like density of charge, but also it has a phase. And this phase gives additional degree of freedom where you can do the same job more or less with much smaller number of elements, for example. But in addition, this S here in CMOS stays for semiconductor. So it's a device which allows you one electric current to control another. In some sense, it's a nonlinearity. It gives you nonlinearity. It means we need also nonlinearity in our system. And so you need to mix this wave with nonlinear properties, and then you need to choose which wave would be good. And it seems to be that magnonics, spin wave, is a very good choice because we can scale everything down to CMOS sizes, to 7 nanometers, frequency gigahertz to terahertz range, temperatures you can do it at millikelvin, you can do it at room temperature. So everything is here, and spin waves are very nonlinear. So in past, it was always the largest problem that nonlinearity. RF devices did work properly, but if you don't do it properly, you can use this as advantage. And here just to report the last such a big milestone we reached on this direction, which gives us already an understanding how good is this direction. It's a directional coupler, and we made a half adder based on the directional coupler. So it's such a device. It has 2 waveguides, one unique waveguide, if you can see it under the map, and here another. It's iron garnet, 350 nanometer wide. And then we send signals through this U-shaped antenna, excite spin wave here, and that's propagate. And this color map is a brilliant light scattering spectroscopy experiment. So red means large spin wave amplitude, blue means no spin wave, and you can clearly see that spin wave runs and then it jumps due to dipolar coupling between the waveguides, brings all its energy to another waveguide and propagates. And here we have So this works as a normal directional coupler, which is known from optics, microtechnique, and so on. But what's interesting about this particular one, that it was first of all already 100 nanometer scale, but second is nonlinear phenomenon. I told you that we need nonlinearity, and if you have zero power, then what you do, the same technology experiment, the same frequency, you just increase power by 10 dB, and you see that spin wave jumps back. So what happens with increase in power, you get a shift in dispersion curve, and then you change coupling between these two waveguides, so coupling length is changed, and you can guide wave back. And in terms of data processing, it's very cool because original idea of magnon transistor, that was just an absorber, and it means you always lose power. Now you don't absorb anything, so you just send information to one direction or to another direction, and it's just perfect for data processing. And so you never lose anything, and spin wave itself decides where to go. And so then we use this experimental directional coupler as numerically to show half adder. So half adder, it's a device which can add 1 + 1 = 2. It's maximum what it can do, but if you can put million of them, then you can do any mathematics. That's how our computer works. And it consists of two directional coupler, one here and one here. Then we code data into amplitude. So if it's red, it means it's logic 1. We have spin wave. If there is no spin wave, it's blue, it's logic 0. This one splits 50-50, then it jumps back and forth, and it goes to S, sum, output, and carries 0. If you make another operation, 0 + 1, then it will be the same. Again, you will have 1 at the output. The most complex is 1 + 1. Because then all energy goes here, and this directional coupler operates already in the nonlinear regime. It changes its coupling, and as a result, signal goes not to the S but to C, and carry is equals 1 and S is equal 0. And this big progress in the direction of data processing finally gave us a possibility to do benchmarking and to understand how good magnonics in general. And you see, we compare 30 nanometer YIG, this kind of structure. So in general, it's very good. In order to build half adder in CMOS, you would need 14 transistors. So it's a huge circuit, and even for 7 nanometer circuit, the footprint would be 1 by 1 micron because it's very complicated. In our case, we have only 3 nanowires and fancy physics inside, but we also need to put here an S, so we need an amplifier. But still, we can analyze that footprint would be the same for 30 nanometer YIG as for 7 nanometer CMOS. Energy consumption, we really are very favorable in terms of energy, 2 attojoule instead of 35 in CMOS, but we need amplifier, and the best amplifier seems to be voltage control magnetic anisotropy based parametric amplifier, which should give us, this is theoretical estimation, it's not even simulated, yeah, just theory, therefore be careful, but it tells that it should give us 3 attojoule. So altogether we are like 7 times smaller energy in terms of compared to the latest CMOS which is on market. And we are slower, so we need 80 nanoseconds, while CMOS, they operate, if clock rate is 3 gigahertz, it means they need 0.3 nanoseconds, so 50 to 100 times faster. But principally, if they would find a solution for heating, they could process data within 60 picoseconds. So CMOS is amazing. But this delay is also just for this concrete realization. So we know now where we are. What's next step? So for example, we got with, in contact with Fabrizio Riente from Polytechnical di Torino, and he split this directional coupler into bits, added some signal amplifiers, normalizers, and built 32-bit magnonic ripple carry adder to show that you really can build very complex circuits with it, and that it works. But now we can say that principally these numbers are quite good. So I know so many so-called beyond CMOS technologies which are working with ampere currents or in Hertz regime. So we are really cool that many parameters can be comparable at least to CMOS, maybe even a bit better in terms of energy, but it's not enough to wake up, of course, Intel. But recently we've got the reinforcement, and here I would like to show you inverse design magnonics also very briefly. So inverse design, it's an approach which is used everywhere nowadays. For example, we have found also in optics. So but then we just translated the same kind of, use the same approach in magnonics. And just to explain it, we can start with demultiplexer. So you have such device. This is working area 1 by 1 micron, split it into cells 100 nanometer. You have one input, and two outputs, 1 and 2. And then you send two signals, F1 and F2, two frequencies in linear regime, they are non-interacting, and you want to have F1 here and F2 here. Then you split it into this number of elements. And what you do, so this is all simulated for YIG, for that structures which we can fabricate. So it's purely numerics, but it's kind of realistic numerics. And what you do first, this is a block scheme how we process. First, you just randomly remove YIG and put air in there. And afterwards, you perform numerics and you calculate how much output of F1 here, F2 here, F1, F2 here. And then you define such objective function, which means that simply you want to have signal F1 at output 1 as much as possible, F1 at output 2 as small as possible. And you multiply it, F202 is maximum, so second frequency goes here, and parasitic transmission F102 is minimum. So you define this objective function, you calculate it, and then you go into the cycle where you just take randomly one of these sectors, you remove YIG if it was with YIG, or you put YIG back if it was with air. You again calculate objective function. If it's better, you keep it and you just go to the second circle and change another state. If it became worse, you just put a state back, and then you repeat it as many as 100 times, 10 by 10 modes. This is one iteration. And after one iteration, you see that objective function jumps from 2 or something till 14. And afterwards, you can still optimize it a bit. And this is the final result. Yeah? So it just places this voids where it's necessary. And you see that the multiplexer works perfectly. 2.6 gigahertz goes to this arm, 2.8 gigahertz goes to this arm. In the same way, you can do multiplexer. Or here are the animations. And principally, the message of this paper, this Nature.com, is that you can do any operation. And just to demonstrate that it's any operation, I said that nonlinear switch is important for devices, and we did it. So half millitesla excited field signal goes here. For 2 millitesla, 4 times smaller, all goes here. The only issue that we had to increase the length of this region twice because nonlinearity needs some time to accumulate. And it works perfectly as a nonlinear switch. Then we know that spin waves are non-reciprocal, and it's kind of advantage compared to optics and electronics. And we just, again, the same structure, we didn't do anything, we just changed objective function. We wanted signal from 1 to go to 2, from 2 to 3, from 3 to 1. Chi has found a way to do it. Chi has developed all this and kind of shown that it really works. And we've got Y circulator. Afterwards, she has shown that also if you decrease sizes 10 times, it stays there. If you change sizes a bit to introduce that imperfections from fabrication, everything works. So it's very powerful device approach, and we show that it's scalable. You can process any data, and very good that for directional coupler it took us, I don't know, 2 to 3 years to develop, and here it took 2 months to simulate everything. So it's very fast and suitable for any processor. For RF, for binary logic, or also for neuromorphic computing, please also check paper of Georgi Saba, Nature.com, the same year, it later published, where he used it for neuromorphics. Therefore, I think inverse design will improve all that numbers in table at least 10 times, especially speed, maybe even better. So we will try that. But finally, I came to the main part of my talk. It's out of plane nanomagnonics. And here you see the waveguides, so it's remarking waveguides which we are working. So nowadays we can go down to 50 nanometer, but the qualitative change happens when you reach around 200 nanometer size. If it's YIG, like 50 nanometer SIP, what happens there? Your waveguide is getting a single mode waveguide. So the problem of micron scale, so-called magnonics, when your waveguide is 2 micron, or so typically was used. Permaloid is that you have always at the same frequency, you have always higher width mode. And then doesn't matter, your antenna will excite them if you will try to bend it, or you will get some inhomogeneity. All these higher modes are generated, and then you operate simultaneously with many waves of the same frequency but different wavelengths. You cannot get any information about phase. Simply doesn't work. And solution was very simple. You need to go to sizes below 200 nanometers, and that's what we name nanomagnonics, yeah, because then you operate with single mode, nice waveguide, and everything is much better. And we studied this waveguide 50 nanometer wide for backward volume geometry when it's magnetized along. we studied it for Demon-Eschbach when it's magnetized perpendicularly. We have shown that the Demon-Eschbach is much faster spin wave and can run 8 micron, even in very flat dispersion, which is happening in such a narrow small waveguide. But we never tried out of plane magnetize. Why we didn't do that? Because there are theories shows us tensor of magneto-optical efficiencies of scattering, Brillouin let's cross-section scattering is 0 when photon is flying along the magnetization direction. So we simply were always confident that BLS is blind for this configuration. But she said, okay, maybe when we have a nano waveguide, we have break of symmetry and so on, maybe we can get something. And he modified a setup and he measured and he came and said that, look, I have practically as strong signal as for in-plane, which was a big surprise for us. And now I didn't prepare slides. Paper is will be placed in a few weeks on archive. But what's going on there is that we have found that in this case we can excite easily very strong precession angle. So usually magnetization precession angle is 1-2 degrees. If it's 3-4 degrees, it's already very nonlinear. In this case, we have 50-degree precession angle. And if you have 50-degree precession angle, easily can excite with very small, with normal microwave power. Then you should take into account also magneto-optical phenomena of higher order, which are usually ignored for in-plane BLS. So we need to redevelop a bit BLS. So the scattered light happens, it changes polarity. So usually magnon scatters phonon with a shift of polarization by 90 degrees, but it's linear light. This one in this configuration, it switches it to elliptic precession and with another angle of polarization. So everything slightly different, but for us it's important that it works. And we tested everything, so we really know what's going on there. So it's all good. Then what we kind of first experiment which we did. Sorry, my mouse is frozen. Okay, so it's very simple. You take this 2 micron white wave, 200 nanometer white waveguide, 40 nanometer thick. You magnetize it perpendicularly, and you put very large antenna. And you know that large antenna means that you cannot excite short wavelengths. So I mean, it's one of the maybe the most advanced in terms of excitation of exchange waves. But here we use completely different mechanism. We use this nonlinearity to excite high K waves, and it works very simple. We have very broad antenna, and usually you cannot excite, so like 2 micron wide. You would not excite wavelengths smaller than 2 micron. But since but it's very good for excitation efficiency. It's large, it's efficient, large region is irradiated, and so on. No problem with ohmic resistance. We apply here using forced excitations, this magnetization precession, very large angle. And when we have very large angle, we decrease magnetization. When we decrease magnetization, we have DMAG here. Yeah? It's out of plane magnetized. It means the dispersion is shifted up, like it's shown here. So under antenna, our dispersion is shifted up, but far away from antenna, this is the original antenna. And then you shift it up, you excite here very large K, like a lambda infinity, like a FMA on the antenna. But then when it goes outside, it transforms, and we can get down to 200 nanometer wavelengths in this excitation. We have shown for COFAP, you can do it much more efficient, and you can get 50 or so nanometer wavelengths. So this is just an example which we already measured in the experiment. So 220 nanometers. So everything is going just on conversion of dispersion. And this conversion is not done by width or by temperature or by other means which people did, but by spin waves itself. It modifies media. And here you see the excitation field of antenna. Here you see the internal field really on the antenna. It's very large. Therefore, we excite here very large K. Then it immediately jumps to K290. And then it transforms to wavelengths 290 nanometers, then it transforms to 130 nanometers. So that's already exchange wave, which is faster. And we see the pre-pass is much larger than it is for dipolar. Yeah, and here is more or less this conversion. So here it's dispersion on the antenna, just next to antenna, and then at 2 different points, but pay attention to this angle. So we have in the linear region it's 1 degree, but on the antenna we have more than 50 degree precession angle, and it gives us such a huge frequency shift of 2 gigahertz. In past it was like tens of megahertz or so. Now we have really something new, and it's possible only because of nanoscale waveguide, because when it's nanoscale, it means we suppress 4 magnon scattering and 3 magnon scattering. So only because you at nanoscale you put down all this parasitic nonlinear phenomena, you can use that one which you need on purpose, and it became very strong for the first time. We never saw something similar. By the way, Demokritov just recently published paper with similar approach, but I think they use larger structure and they got 10 or 15% angle of precession. But here we show that at nanoscale it can be much larger. So that's what we achieved. Now, how you can do it? You can go, of course, try to think further. So it's not only very long propagating exchange waves, because it's already far away in K, it's getting faster, it runs longer distance. We measure now, I don't know, tens of microns without problem, this wave, away from antenna. And we have very strong nonlinearity, which can be used for something, but also we see fold-over effect. So, for example, here is spin wave intensity, which we measure. We apply 10 dBm power, and we change frequency. So we go from the left side, we pump above the dispersion, nothing happens, and then we start exciting. So when we go here, spin wave already is a bit above our excitation. And what we do, we can shift dispersion. So kind of when we switch frequency, we keep system hot, and we just additionally shift more down, more up dispersion. But at some point, we are not able to anymore to shift it, and we stop generation. And then when we go to higher frequency, there is no more generation. Now, when we go back in frequency, what happens when we are reaching this point, system is cold. We did not have high angle of precession before, therefore you cannot trigger magnetization precession. It doesn't work, then you go, and only when you reach this frequency around 6 gigahertz, you can again trigger it and it starts to precess. So we have such fold-over effect. Like history is in power, principally known for as a mechanism of spintronics. But what does it give us? Give us the following experiment. We can now work with two different signals. One can be named the CV, like power for our signal, and another is trigger pulse. How does it work? So the signal line, principally we want to keep it CV, but since we need to repeat this experiment, what we do, we just split in such very long 1 microsecond long pulses, and then there is just a such short period without pulse where we kind of reset everything. We can repeat the same experiment periodically, but it's in principle CV, and we apply it at 6.4 gigahertz here, and you see that nothing happens. So when we apply it, the output is equal to 0. We cannot excite anything when we apply that signal. Then what we can do, we can apply such very short 50 nanosecond long trigger pulses at this frequency where we can excite. And you see when you excite only trigger pulses, you can get real excitation of spin wave at the points where you excited it. 50 nanosecond long, it disappears. But when we apply both of them, this CV and then trigger, what happens, you trigger magnetization precession at this point and it keeps it until the reset pulse. Yeah, and we have nothing, and then you have again. So we really show that with this short trigger pulse, we can switch system from no precession to there is precession. Then we just tested it, so you see that you can apply this trigger pulse at different point of time. It all works as I predicted. You can code into different state, 111, 101, 1001, and so on. You can trigger. And I'm coming to the last my slide. Yeah, and then what we have found that output intensity of spin wave depends on the power of trigger. And this was really surprised because trigger is either on or off. It should not be this slow. And afterwards we have realized that that's because it's probabilistic process. So this triggering, it depends on the power. For large power you have large probabilities, and we just measured it directly. For large applied power, you can always practically each experiment you switch it on and only time to time off. And for small power, only time to time you switch it on. And it opens access to stochastic computing, and which we are developing now. And yeah, so I would like to attract your attention to this roadmap of spin wave computing. It was organized in a self-organizing method, so everybody who wanted could contribute. We've got 116 authors, a lot of different directions, including 2D, 3D, magnonics, slow power amplification, Boolean logic, neuromorphic and conventional quantum logic. So if you're interested to know what's going on now, what people are thinking where they believe all this moves. Please have a look. It just published 3 weeks ago. And with this, I would like to conclude. So first of all, I hope I could convince you that inverse design is a big new issue because it's very powerful, it's very fast, and it's suitable for everything. Just question how large matrix you have. And I hope I could show you that out-of-plane magnetics is of high potential because it's isotropic transport, it's deep nonlinearity, it's long-distance exchange waves, it's stochastic computing, and so on. And with this, I would like to thank you for attention.
Thank you very much, Andrii, for your nice talk. So questions, I see, I think Professor Oliver Klein. Oliver Klein, go ahead to ask a question. Yeah.
Hello, thank you, hello everyone. Thank you, Andrii, for this nice talk. I have a principal question at the beginning of your talk about the trade-off between the speed. You see, I guess the computing time that you give for the speeds are linked to the spin lattice relaxation time. This is the limits of how fast you can operate this Magnonics device. And okay, but this question is intrinsically linked also to nonlinear threshold. That means the shorter is the relaxation time, the more difficult it is to reach the nonlinear regime. So, so what do you think is really the trade-off between how much power you can use and the speed?
Thank you very much. I'm very glad to see you in the non-live form. It's not the first part is not exactly like you said. So what limits our speed of device? We just measure the propagation time. So it's time which spin wave propagates from this side to this one, and we need 80 nanoseconds, and that's the limit. In terms of, and that's why I say that for this one, which is like 10 or 100 times shorter distance, and if you do the same job, it will be simply 10 or 100 times faster data processing. And in terms of alpha, you're absolutely right. There is a coupling between alpha and nonlinearity. The smaller alpha, the better nonlinearity, the better everything. But it's also better for us because we don't want to lose anything. We need some compensation. So if it's, let's say, all Magnon circuit, you don't have converter to electric current. You put million of this, I always say, of this elements, but time to time you will need to put amplifiers. And this alpha, small alpha, means also that you will need less amplifier. Therefore, kind of it puts us that small alpha is good. So we need to search for new materials for ECO, maybe something better. Cobalt iron boron is very good nowadays. And we need small alpha, which will increase speed and will improve nonlinearity.
But you agree that the propagation time, okay, is you cannot operate another operation within the relaxation time. Like you cannot switch states. The limitation is really the relaxation time, the speed.
No, your relaxation time should be much larger than propagation time. Than operation time. So if your Magnon leaves 1 millisecond, just do job within 1 nanosecond, and it will be ideal situation. So it puts a limit, but we usually much shorter, yeah, here. So already than a lifetime of Magnons. And another way to increase speed is to increase velocity. That's why this work of Haiming is very important, and the Grundle and Minzonku and everybody, because then you can work with fast exchange wave. It means it runs faster, and then you can again improve the speed of your device.
Okay, thank you.
Thank you. Maybe one quick question from Dr. Sadovnikov. Please go ahead, ask a question. Yeah.
Yes. Hi, dear colleagues. Do you hear me?
Yes. Good.
Thank you. Thank you, Andrii, for a very good talk. So it's good for opening of this conference, this kind of questions. So, Andrii, I have a short question. First of all, I would like to hear your opinion about this kind of magnetization. So last years, it was a trend that we study the tangentially magnetized magnetic films, no, mainly. so in daemon configuration and so on. So now it seems that perpendicular out-of-plane magnetization is also interesting. And also the question is about your ideas with nonlinearity below the antenna, under the antenna, and far from it. Yes, how do you take into account the dispersion in yttrium iron garnet, which is metallized? So on magnetic metallic film put on top of the iron garnet. So it should somehow maybe change also the dispersion. I think maybe I'm not right, so but in this direction. So
very much for this. So time is running, then I will try to answer very quickly. Yes, thank you for the question. You're right. Here we have metallization. As far as I remember from Gurevich-Milko, it doesn't change much dispersion for backward volume and for forward volume slightly. It changes a lot dispersion for them and airbag, which is not the case. Therefore, I would say it should not influence much except introducing new damping mechanism, but I would double check it. Thank you very much for this point.
thank you. Thank you.
Thank you. Thank you. Thank you, Andrii, again for the nice talk. Because of time, we move on to our second presentation. It's an invited talk from Professor Teruo Ono. The topic is 3D domain wall motion memory with artificial ferromagnet. So please.
Okay, thank you very much for nice introduction. Can you hear me?
Yes, clearly, yes.
Okay, good. So let me start. So today I'd like to propose a three-dimensional domain of motion memory with artificial ferromagnet. Yes. Sorry.
We can hear you, but we cannot see you.
Oh. Video is on now, and I have a problem. My slide doesn't work.
Maybe you can stop sharing and try again.
Okay. Okay, good. So this is the collaboration list. So in addition to my group of Kyoto University, we have several collaborations. For microfabrication, we have the collaborations group of Nagoya University and the National Institute for Material Science. And we are using electrode deposition techniques for this research from the group of Tokyo Institute of Technology, Waseda University, Keifu University. And we have also the collaboration with theorists, simulation by Shuta Honda of Kansai University, and we have also the signal processing group of Ehime University. And I'd like to acknowledge to all the people in my group in this photo. Okay, let me start the background on my research. As you know, this is a schematic illustration of memory hierarchy. Okay. So in general, high-speed memory is expensive and has lower density like this. And especially between the gap between main memory DRAM and the storage like SSD is a huge issue because there's almost 3-digit speed gap. So there's a strong demand for new memory bridging this gap. And as you know, one of the candidates is the so-called magnetic racetrack memory proposed by Stuart Parkin of IBM. So he proposed this kind of 3-dimensional spin-lock storage memory in which we can store information as a direction of each domain. And importantly, we can shift all the data by injecting electric current paths back and forth. And IBM claims this types of new memory is the capacity of hard disk drive and also has a reliability and performance of solid state memory like DRAM, flash, or SRAM. Actually, in 2004, we demonstrated actually we can push the domain wall by injecting electron pulse like this. This is a kind of successful magnetic force microscope images of domain motion. So in this case, we use in-plane magnetized permanent film. And actually, the group of sphere parking demonstrated racetrack memory version 1 by using in-plane magnetized permalloy alloy plus spin transfer probe, like our case. So you can see here, the domain wall can be displaced by using direct current pulse. The next generation, version 2, can be seen here. We use perpendicular magnetization, in this case, cobalt nickel multi-layer. We also push the domain wall in this perpendicular magnetization by using spin transfer torque, STT. This is a demonstration by using MFM observation. And also, we demonstrated we can electrically detect the domain motion by measuring a normal Hall effect. So here we can say the domain motion can be achieved with lower current than in the case of using in-plane magnetization formula. So this is the second version of racetrack memory. And another development is done by using Jaroszewski-Moria interaction and spin orbit torque. In this case, we put heavy metal like platinum on top of perpendicular magnetization, such as cobalt. In this case, you can inject spin current by using spin Hall effect in heavy metal layers. And the injected spin can exert a torque on the magnetization inside the magnetic domain wall, so we can move a domain wall in this wire by using spin orbit torque. And this technology gives us a more higher domain velocity. In 2015, again, the group of sphere parking gave us a new technique. Means they use so-called synthetic antiferro, like this. In this case, they use magnetic layer sandwiched by the selenium, and they coupled antiferro molecule like this. And in this case, they can achieve higher domain velocity. And nowadays, there are many reports they get higher velocity beyond kilometer per second. Okay. Then they propose three-dimensional racetrack memory by using synthetic antiferro plus spin orbit torque. So here you can see a domain or injector here and many domains in a perpendicular wires, and the data can be read out by using MTG like this. But you see, if you see carefully the figure, then you notice this is this thread. This is a kind of substrate. So it seems to just make this one horizontally and put it vertically. So there are several issues to be solved. First one is how to make this kind of three-dimensional structure from this kind of substrate sputtering techniques. And also, there are several issues how to control domain wall position precisely usually it's very difficult to control domain policy precisely. And in some case, we do domain walk and elucidation of domain walks. And how to reduce domain of motion current, and also how to write. Here we can see the domain of injector, but we don't know how to do it. So now I want to propose new type of 3D domain of motion memory with artificial ferromagnet. I mean, artificial ferromagnet, this pillar. This pillar consists of two kinds of magnetic layers. One has perpendicular magnetic anisotropy, and the other is with no magnetic anisotropy. So you can store your bit of information in this bit layer, greens, and yellow layer serve as a domain layer. So shortly speaking, this is a kind of 3D memory with as many bits as bit layers, green layers per column. So the operation principle is as follows. So now this is a cross section of one column, and we have 12 layers here, and we have 6 bits. In the initial state, all the magnetization directs downwards, so we have 0 bits in all layers. So writing is the following. We just inject current pulse in lighting wire, then we can switch the magnetization in this layer by SOT switching. It means now we have a domain wall in layer 3 here. Okay, so the bit information is now 100000. And then we shift this information upwards by injecting electric current pulse through the layer, through the column. Also in this case, we push our domain wall from layer 3 to layer 9. And then we write again by injecting current pulse for writing wire like this. By cycling this process, we can store information as we like in this period. And reading information is really easy. So we push our information by injecting a current through this column, and then we detect the direction of magnetization of this topmost layer by MTG. So we can read out all the information simultaneously. So this is a kind of shift register. It means all bits information can be accessed with only 2 wires, bottom and top, because we can shift all the data by the current. Okay, so here I'd like to compare our structure with 3D NAND memory, semiconductor memory. So as you know, so this is a 3D memory with many pillars. And so here are a lot of cells which can be accessed by these transistors. It means we need to wire to each cell. So because of it, this memory has a complicated structure, and there are so many layer structures. But if you see this structure, because this is a kind of shift register, we can access all the data in a column just by 2 electrodes. So there's no need of wiring to each bit. So there's a big difference in these structures. Okay, then we verify the operation by using simulation. Here we have 12 layers. So this is parameters for bit layer and domain layers. And the scale is like this. Diameter is 20 nanometers, and each layer has 3 nanometers. Okay, so the first we check the domain width in artificial film length. We set our domain here and do the relaxation and see the width of our domain wall here. And this is the result by changing the domain wall exchange coupling. By reducing the domain wall exchange coupling, we can reduce the domain wall width down to 1 layer thickness. So it means less than 3 nanometers. So we have a small domain width, and it is tunable, and which is very good for achieve high stress density. Then we check the shifting operation. The parameters here. We applied 2 nanosec, 4 times 10 to 10th amps per square meter current pulse. First, we set our domain wall layer 3, like here, this, and then we apply pulse current. And then you see the change in magnetization. So the blue line is the magnetization of our domain wall here 3, and it switched up. And now we have a domain wall in layer 5 here, green lines. And we can push it again to forward from 5 to 7 and 7 to 9. So we can shift our domain wall. And importantly, domain wall position can be always be controlled in a domain wall layer. So we can do the precise control of domain wall position. So, and we check the effect of exchange stiffness in domain wall layer on JC. We set our domain wall layer 5 and push the domain wall by increasing the current density, and we determine threshold current density for this domain wall motion. So this is the graph which shows the threshold current density is a function of exchange stiffness in the domain wall. So as you can see, by increasing the exchange stiffness a bit means around several picojoule per meter, we can reduce the current density for the domain motion more than 2 orders. So here we have the current density of about 10 to 10 amps per square meters. So we also checked the thermal stability. So here again we set a domain wall in layer 5, and we increase external magnetic field and check how large magnetic field we need to depend the domain wall from layer 5 to layer 7. So this is the thermal stability check. So first, please focus on this red axis. That means the deepening field of our domain wall from layer 5 to 7. Of course, by increasing the this is the Ku anisotropy in a bit layer, in a green layer. The deepening field of domain wall is increasing from 0 to about 400 millitesla for the perpendicular anisotropy of about 15 times 10 to 5 joule per cubic square meter, cubic meters. Okay, but JC is more or less constant up to 10. And then we also see the increase in threshold current for the memory motion by increasing the multi-anisotropy in storage layer, bit layer. But if you tune in this region, then you have large deepening field with very small threshold current. For example, if you choose this data, it means a deepening field of 138 millitesla, which means almost 200 larger than the room temperature energy. It's okay for 10 years retention with very low current. Okay. So here I would like to propose fabrication technique of 3D domain memory with cheap cost. So this is the channel structure of 3D NAND. It is my big surprise to see this figure. They actually control the etch profile in angstrom dimension, while they etch out to the micron scale. So there's a nanometer hole with microns long. So how about making the wires in this hole by using electrode deposition? So actually, almost 20 years ago, there's a report we can make such a very narrow, long wires by using electrode deposition technique. So we can make many column pillars into the 3D NAND structure by using electrode deposition technique. Okay, last part is benchmark. So speed. According to our benchmark, it's 100 times faster than 3D NAND. It's comparable DRAM because writing, reading is almost nanoseconds, and shifting is very fast, and all things seem to be limited by wire delays, which is comparable to DRAM. Density should be comparable to 3D NAND because we use 3D NAND fabrication process. And the power is comparable to MRAM, means it's 100 times smaller than 3D NAND. And cost is also attractive, which is more than 10 times cheaper than 3D NAND because no need of wiring to each bit, significantly fewer process compared to 3D NAND. And also we propose the use of inexpensive electron deposition technique. And the derivatives are comparable of MRAM. Retention characteristics should be the same MRAM and HDD. So this is the figure of the benchmark. As you can see, this new memory high potential that deviates from conventional trend. Conventional trend means higher memory, high speed memory should be expensive. Now this is because our proposed memory has 3-dimensional structure and non-volatility of multi-material. And as you know, multi-material has a very high speed dynamics. And also the memory has multi-level memory with shift resistor structure. These properties of new memory lead to the comparable speed of DRAM and comparable density of 3D NAND, and 100 times smaller power compared to the 3D NAND, and 10 times cheaper compared to 3D NAND. And this is my conclusion. Thank you very much for your attention.
Thank you very much. Thank you very much, Professor Ono. Any questions? And I have a question concerning the domain wall motion. So you mentioned it's very important, but very challenging to have the domain wall move in the high speed in kilometer per second. So what determines the upper limit of the domain wall velocities? And is there any way we can go further?
Okay. So theoretical limits are given by the speed of spin wave in the material. So you can consider a domain wall as a wave packet of spin waves. So then this domain wall wave packet has a maximum velocity which limits by the spin wave. It's usually several kilometers per hour, kilometers per second, and this almost limits.
I see. Thank you. So we have a question from Professor Hicken. So Rob, please. Yes, please go ahead and ask questions. Sorry.
Okay, thank you very much for your talk. If I understood correctly, you place a magnetic tunnel junction on the top of the pillar, but
yes,
you pass current through that tunnel junction in order to shift the bit within the stack. Isn't that going to be a problem in terms of electromigration because of the large current densities that you need?
Yeah, good point. So that's why we have to reduce the current down to maybe the several 2 or 3 times 10 to 11. So actually, current envelope technology demonstrated we can throw the about 10, 11 amp/pascal meter current density through the MGO for switching in MRAM. So I think it's okay.
Okay, thank you.
Thank you.
Any other questions? If not, then let's thank Professor Ono again. Thank you. Yeah.
Thank you very much.
Thank you. Thank you. Then we can try to move on to our next talk. Dr. Ustinov.
Hello.
Hello.
Hello, everybody.
Maybe you can share the slides. Very good.
Okay, do you see my presentation?
Yes. You can put it in play mode. Yes. Very good. Okay. Okay. So yes, our next talk is from Dr. Alexey Ustinov from St. Petersburg Electrotechnical University. His topic is microwave nonlinear phase shifter controlled with pumping spin wave. Please.
Okay, thank you, Chairman, for introduction. I would like to thank also conference organizers for my invitation to make this presentation. I start with motivation, then I will discuss experimental setup, experimental results, and numerical simulations. Okay, so as is well known, spin wave phase shifters are basic elements of many spin wave circuits. For example, magnetic logic circuits and circuits for neuromorphic computing. They could operate in linear regime, and it was published in many papers. Less attention was given to magnetic logic gates based on non-linear magnonic phase shifters, and recent advances in this area are development of some elements based on the structure similar to spin wave delay lines or phase shifters for neuromorphic computing. Typically, magnonic phase shifters is fabricated by such a way that phase shift produces due to changing in bias magnetic field. One more promising approach for fabrication of magnonic phase shifters is to use an induced nonlinear phase shift. Let us consider how it could happen. This figure shows magnetization precession, and if we increase spin wave amplitude, we reduce static magnetization of magnetic film. Therefore, if we excite spin wave at the particular driving frequency, let's call it as pumping frequency, then we will have nonlinear frequency shift of the spin wave dispersion, and therefore we will have induced nonlinear phase shifts of the waves at the different frequencies. This we can call it induced nonlinear phase shift, and this induced nonlinear wave number shift, and this induced nonlinear wave number shift produces the nonlinear phase shift. Therefore, purpose of the present work is to study a nonlinear phase shift of low power spin waves propagating in magnonic crystals induced by high power pumping spin waves excited both inside and outside the magnonic band gaps. This slide shows experimental setup. It is on the left small signal operating wave is produced by vector network analyzer, and high power pumping spin wave pulses was produced by RF generator, and these two signals are excited by microstrip antenna simultaneously in the magnetic film. A detailed look of the measurement cell is shown here. So we apply to the input antenna so-called probe signal, small power probe signal and high power pump signals, and observe at the output antenna what happened with phase shift of the small power probe signal, which we consider for phase shifter as operating spin wave. And when we developed original measurement procedure using vector network analyzer in order to measure the phase shift of operating wave, we switch on VNA in the time domain operation. In this case, when pumping signal is switched on, we observe change in the phase of the low power operating signal. Details on magnonic crystal structure is listed here. So we used yttrium iron garnet film having thickness of 5.5 micrometers. We etched grooves, 10 grooves in order to produce magnonic crystal. Width of grooves was 50 micrometers and period of structure 300 micrometers. And we put antennas directly in the beginning and at the end of the magnetic crystal. So we excited spin wave directly in the magnetic crystal. In other words, distance between antennas equal to length of the magnetic crystal. And now we consider experimental results. This figure shows amplitude frequency characteristics. Black line shows experimental characteristic, and red curve shows theoretical amplitude frequency characteristic. We perform calculation taking into account excitation and reception efficiency of spin waves by microstrip antenna, and also we added losses to losses of spin wave propagation in magnetic crystals. We see that these characteristics are in good agreement, and then we carried out measurements in such a way. We we apply this operating wave with frequency f1 at different frequencies, f11, f12, and f13. And simultaneously, we applied pump signal at different frequencies. These frequencies were both inside magnetic band gaps and outside magnetic band gaps. For example, for f11, we applied pumping pulses at the frequencies somewhere between first and the second magnetic band gap, inside the second magnetic band gap, between the second and the third magnetic band gap, and at the third magnetic band gap. And what we obtained, this figure summarizes results of the measurements of the induced nonlinear phase shift. So we see that the phase shift for pumping frequency inside magnetic band gaps smaller than outside magnetic band gaps. And crosses show here the phase shift measured at the regular waveguide. We just shifted magnetic crystal, we just shifted magnetic film, we shifted region of magnetic crystal outside here. So between antenna was a regular part of the magnetic film. So we developed, next slide will show details of these results, and points show here how this induced nonlinear phase shift depends on the power of pump signal applied at different frequencies, and we see that at the frequencies of magnetic band gaps we have a little smaller induced nonlinear phase shift. We have carried out set of measurements at the different frequencies of small power operating spin waves, and obtain this data. We also have developed theory describing this behavior, and next slide I will discuss on the next slide details of this theory, but I can show you here that lines show results of numerical simulations, and numerical simulations describes very good the observed behavior of the induced nonlinear phase shift. We developed theoretical model based on nonlinearly coupled Landau-Ginzburg equations, and these equations are coupled by nonlinearity. Terms which describes nonlinear coupling are here. So then this is description of the standard coefficient of this equation. I will not discuss it here. These details are published in our recent paper in 2021. And this is the last slide showing what happens if we apply pumping spin wave inside the magnonic band gap. So this figure shows qualitatively situation without damping. So we have damping of pumping wave due to power transfer from this forward wave to the reflected wave. If now we take into account damping, in the case of exponential damping, we have this curve. If we have nonlinear damping, we will have additional attenuation. And if now we will take into account this power transfer from forward wave to reflected wave, we will observe this additional attenuation. Using this approach, we calculated curves on the previous shown on the previous slide, and also we carried out comparison of the induced nonlinear phase shift, and it is shown here. So we see that inside magnonic band gaps, the induced nonlinear phase shift is smaller if pumping frequency inside magnonic band gap. And this graph simulates output pumping power versus input pumping power calculated with this theory. We see that as it is easy to understand, if we apply spin wave pumping signal at the frequencies inside magnonic band gap, it will have much higher attenuation. So this is conclusion. So induced nonlinear phase shift is reduced at the frequencies inside the magnonic band gaps due to an additional damping of pump wave caused by power transfer to the reflected spin wave. And the second, spin wave phase shifters based on this phenomenon could become a fundamental building block of magnonic logic circuits. Thank you for your attention.
Thank you for the nice talk. Because I'm one quick question. Okay, so if not any because of the time, so we move on to our next talk. Thank you, Dr. Ustinov. Yeah.
Thank you once again.
Okay. So our next speaker, Dr. Matveev. Great. Dr. Matveev, can you hear me?
Yes, yes. Can I start?
Yes, yes, very good. So next talk is from Dr. Oleg, Matveev Oleg from Saratov State University. His topic is spin waves in nanoscale periodic ferromagnetic waveguides. Please.
Thank you for the introduction. Greetings to the conference delegates. I present the work performed at Saratov State University with the, together with the Moscow Institute of Physics and Technology. In this work, we present results of experimental and theoretical investigation of spin wave propagation in nanoscale yttrium ion GaN waveguides. This material was chosen because it has low-level losses, the possibility of scaling up to several nanometers, and low energy consumption for excitation of spin waves, and the miniaturization of components and reducing of power consumption are the main challenges in novel magnetics. For the theoretical calculation, we use the model in the form of dispersion equation that was introduced by Kalinikos and Slavin, and later it was often used to simulate spin wave propagation in thin films. This model is taking into account the exchange direction as well as finite width of film, which also makes it possible to simulate with modulated structures. In this slide, several dispersion curves are presented for different magnetic Bias field. We can see the shift of spin wave band with the magnetic Bias field for different film width. We can see that excitation of width modes affects the dispersion of long waves. And for different thickness of films, we can see that decreasing the thickness reduce the width of spin wave band. Next, we used this equation to simulate periodic structures in which areas with different parameters alternate, and respectively in such areas spin wave propagate with different wave number K1 and K2. Thus, we can simulate width modulated structures in which areas with different width alternate, as well as depth modulated structures in which areas with different thickness alternate. Solving the equation gives the inherent dispersion characteristics with the set of Bragg band gaps at Bragg wave number, where L is the period of structure and M is the number of Bragg resonance. In the band gap, spin wave cannot propagate, what is evidenced by the presence of the imaginary part of wave number painted in red in the figure. Let's discuss the experimental studies. For the experiments, we used yttrium ion GaN film, epitaxially grown on a gallium gadolinium garnet substrate. Thickness of yttrium ion GaN film is 100 nanometer. Saturation magnetization is 139 Gauss. For magnetic resonance line width is 0.5 stat. This picture shows the atomic force picture of film surface. Formation of yttrium ion GaN waveguides and antennas for excitation and reception of spin waves was carried out on the basis of the Institute for Physics and Microstructures of the Russian Academy of Science in Nizhny Novgorod. Fabrication took place in several stages. Formation of photomasks and argon ion etching of AEG films for pattern of waveguides with different lengths, width, and modulation of width and thickness. Next, coplanar antennas of firearm with adhesive sublayer of titan were created using the same method of photolithography and magnetron sputtering. Two geometries of antennas were created, type 1 with contacts with 7 microns and gap between them 4 microns, and type 2 with contacts width of 2.5 microns and gap between them of 2 microns. This picture of finished substrate with 16 different structures. In this slide, you can see optical microphotographs of width modulated waveguides with modulation at the edges of waveguide and depth modulated. The features of depth modulated is clearly visible from optical interferometer pictures. The length of waveguides was about 100 microns. For the experimental studies of spin wave propagation, we used a microwave probe station with ground signal ground probes and vector network analyzer. In this slide, pictures of probe station setup is shown. You can see probe, electromagnet, microscope, and network analyzer. And this slide shows spin wave spectra in the investigated structures at different parameters. The spin wave bandwidth is about 100 megahertz at magnetic Beers field from 400 up to 1000 Ørsted. This graph shows the dependence on the waveguide length. We can see that increase the waveguide length by 30 microns leads to an increase in the maximum attenuation by about 2 decibel. This graph shows the dependence on the magnetic Beers field. We can see that spin wave bandwidth decreases slightly with increasing magnetic field. And this graph shows the dependence on the waveguide width and also spin wave spectrum in the width modulated structure with period 4 micron shown by violet curve. We can see that decrease the waveguide width significantly reduce the intensity of spin wave, and we did not observe breakband gap in this modulated structure due to the use of antennas that was not excited the required range of wave numbers, unfortunately. We used the antennas type 1 with contacts width of 7 microns and gap between them 4 microns. The next slide shows spin wave spectra and experimental dispersion characteristics obtained from phase frequency characteristics in depth modulated structure with period 4 microns and depth groups on the surface of 10 nanometer. In these structures alternates areas with thickness 100 nanometers in 90 nanometers. For these structures, we use the antennas type 2 with contacts width of 2.5 microns and gap between them of 2 microns. And we can see that spin wave bandwidth is about 150 megahertz. When compared with regular structure painted by blue, we can see a dip in the spectrum highlighted by gray oval. Analysis of dispersion characteristic shows that it formed at break wave number, what is about 0.8 microns to the minus first power. So we can name it break band gap. This band gap is clearly seen at different values of magnetic Beers field on spectra and experimental dispersion characteristics. Now let's discuss nonlinear phenomena in the investigated structure. The change in the longitudinal component of magnetic moment plays a main role in the nonlinear processes in ferromagnetic magnetized to saturation, and we can take into account the amplitude of the input signal that affects the magnetization in our model, and we can see that band gap shift down in frequency when the input amplitude increases. Similar effect we observed in the experimental study. Band gap shifts by about 10 megahertz with increasing input power up to -10 dBm. In summary, I can talk that we fabricated nanoscale periodic ferromagnetic structures based on yttrium iron garnet films and investigated spin wave spectra using vector network analyzer. We observed a Bragg resonance at Bragg wave number in depth modulated structures. Also, we investigated nonlinear phenomena of band gap shift with increasing of input signal power. Such structures can become the basis of magnetic devices for processing and transmission of information. I thank you for the opportunity to present our work and your attention. Thank you.
Thank you. Thank you for the nice talk. Okay, questions? So Yuelin Zhang, could you let's go ahead and ask question.
Hello.
Yes.
Hello. Yeah, I have a question. Generally, the nonlinear effect is studied on the higher power. We noticed you use a very low power. What will happen if you increase? You continue to increase the power to 0 or 10 dBm.
Thank you for the question. Thank you for the question. We didn't use some gain, and I think so low power at which nonlinear processes appear is because we use submicron films.
Thank you very much.
Okay. Any other questions? Okay. Is Dr. Sadovnikov, please ask question.
Thank you. Thank you. Oleg, how could you associate the absence of band gap on the first structure, which is width modulated? It is associated only with a narrow bandwidth of excitation, or different mechanism maybe inside?
Thank you. Thank you. Firstly, we associate absence with antennas that could not excite spin waves with wave numbers more than 8,000 centimeters. And also we use wide waveguides of 50 microns, and it can be also a reason for absence of the band gap.
Thank you.
Okay, due to the time, thank you, Dr. Matveev, for the nice talk again. Yeah.
Thank you very much.
Thank you. So I think that's the end of the first session. I would like to thank all the speakers in the session again. So based on the schedule, we'll have a break. So about half an hour, we'll come back at 17 p.m. Beijing time. in about half an hour. So see you in a bit.